Welcome back to ECE 442-542. We're getting near the end. You are only going to see one more homework assignment, and that one is going to be optional. This is the last required homework assignment, is homework number 7, which is due, I think, the Monday of the last week of class. Our week is full. We have both lecture days that week, but that particular week, if you're in other classes, stops on Wednesday, the last week. But we have a homework assignment, you have your project due, and I think I may make that optional homework number 8 assignment due on reading day, which is the Thursday. But I need to make that available to you, and that will be dealing with Unit 8 material, which will probably be on the final exam. You just won't be held accountable for that homework. You will be held accountable to the material covered on that homework on the final exam. I did post some additional material based on what we talked about last question. So the homework number 7 is due on the Monday of design. Yes, that's design day. Is that true? Yes. So if you want to do it early, you can. Or let me think about that. Maybe I'll modify. The question was, wait a minute, that's Monday, that's design day. That's usually a really populated class, period. Wow. Compared to this, maybe it won't be that much different, but hopefully I'll see a few bodies in here. Some years, students have brought their winnings in after design day. They carry their checks into class. They give them a big poster board sized check, and that we displayed on the front of the class. I didn't take a picture and upload it, but maybe I should have when that was done, but I didn't. I didn't want to overly embarrass the winning teams. But if you win a check, if you get a check at design day, you can display it in class on the 29th. Let me decide on homework number 7, its due date. Where were we? Additional material. It's on departure angles and arrival angles. It's really based on one of the conditions that you use to sketch the root locus, which is the phase angle condition. That's how you find how you're immediately leaving a pole. That's how you depart, or that's the angle with which you depart the pole. If it's a complex 0, then it's how you arrive at that 0, what angle or what direction you're coming in or approaching that 0 at. And that's helpful in sketching root loci. It's really more helpful for me to grade, or to give me something to grade on the final exam and in homework number 7. The final exam is on a Thursday. That, I believe, is the last day of finals, and it's from 1 to 3 on that last day of finals, May 9th. Today what I want to do is go over PID control. We've talked about P, we've talked about PI, we've now moved up to PID, and I will scroll through basically the derivation. What does that look like structurally? And we'll start talking about some examples. Then we will get into generic controller design. By that I mean now we get to pull down the 2 shakers out of the cabinet, and they have loads of poles and zeros, and you get to shake however many you want onto your plane to try to make your pattern behave the way that you want it to. And how are you wanting it to behave? Obviously you want all of your closed loop poles inside your unit circle simultaneously. And how do you do that? We'll talk about that relative to generic controller design, and it's somewhat based on understanding the root locus. If you want more information on that, that's in the 2 chapters in Shams on control, and you can find that in the course resources section of D2L. Then Unit 8 is actually going to be the state space control design. And that will be what homework number 8 is dealing with. Here is our general diagram for a PID controller, and you'll notice maybe, if you're really paying attention, that I haven't placed an argument inside the brackets for G or C. This could now represent an analog control system or a digital control system, and we're going to look at both. The analog, because it allows us to easily, or maybe more easily, see the P, the I, and the D. Because we can integrate with a 1 over S in the frequency domain, we can differentiate with a multiplication by S, and we can scale P with just a scale or a gain K sub P. And that's where we're going to start. And then we will try to illustrate how we can move from that into the discrete time version of a PID controller. We're going to look at several forms of PID controllers, but here's the one that jumps out at you. If you just needed to write down an expression for a PID controller, this is what I would write down. I would write down a proportional gain. I would write down an integral 1 over S with an integrator gain K sub I, and then I would write down a derivative S and scale that with K sub D. And now you have a P, an I, and a D gain that you have knobs. If somebody hands you a PID controller, which you can now buy these, you can buy these off the shelf, and you can plug them in. You now have various knobs on the front of that, or access to those gains, and you can now adjust those or turn those, and now that's how you can think of weighting the P term. And what's the P term influence? The error at the present time. The I term is integrating up the errors from the past up until now, and the D term is sort of the anticipatory term. The I term is good for removing or improving steady state accuracy, removing error in your system. The D term can be used for speeding things up. Suppose now I factor that a little differently. Or suppose I factor out the gain from all three terms, and now I have a polynomial or rational expression in S scaled by the proportional gain K sub P. So you have three terms still, but now you're scaling all three of those with this K sub P. But obviously the end two terms in there depend on K sub P if you write that gain in terms of K sub I, K sub P, and K sub D. You're going to think I just wanted to go back to algebra class. But now, here's another form. And what's significant here? Now you have a gain that multiplies the S. An S basically has units of per second. Now your T, all these T parameters are now times. So you have an integral time, T sub I, and you have a derivative time, T sub D. And you might be designing your system by adjusting the overall gain of your controller and manipulating the integral time, T sub I, and the derivative time, T sub D. Again, you have three parameters that you're adjusting. And here I've just tried to define some of those variables in these three equivalent forms. Hopefully that didn't wake you up if you're listening to this. You've now triple speeded. I'm going pretty slow right now, but I'm about to fall asleep. Anybody? Somebody was carrying food on the way over here. I just about started following them and asking for a handout. So that sounds empty. There's no food or drink in this room. I didn't see anything. So now we have a proportional gain, integral time with units of second, derivative time, and you can relate those to the case of P, the case of D, and the case of I. What's the digital form look like? Oh, it's obviously like this. You have the input to the system is U of n, and E is the error signal, let's say, between the reference input and the output. And here are how all of the different gains that you saw earlier in the analog setting influencing the different error terms. Now you have the error now, you have the error 1 time step before, and you have the error 2 time steps before. And this U of n equaling U of n minus 1, that's this integral part. This is now storing or remembering what your input was in the previous sample, and now you're adjusting that input to your signal by weighting previous and current errors. And you're weighting those proportional to, well, T here is just the sample period, so you have to figure out what that is based on your system. But once you've picked T, now you have your integral time and your derivative time, and if you wanted to implement a digital PID controller and somebody already had specified or designed an analog PID controller in terms of integral time, derivative time, and proportional gain, all you would have to do is pick the sample period, and now you have the digital PID controller. We probably won't use the digital PID controller in this form, but that's how you could use this form. We're actually going to see how that arises. Where does that expression come from? Or we want to go C of S to C of Z. And do we know how to do that? Hopefully your heads, if they're not already on the pillow, they are moving up and down in the yes direction. We can go from or to discrete from analog with some of our discrete equivalent approaches. And that's what we're going to do. But first, let's start with C of S and manipulate it into a form that's amenable to this discrete equivalent process, which now the way that we're going to do it here is let's go ahead and factor out an integral from all of those terms and push that integral to the other side. Well, let's cross multiply, and now we have in the frequency domain a multiplication by S on our input signal to the plant. And then we have our air signal E scaled by a constant, an S, and an S squared. And we know what happens when we operate on some Laplace transform quantity by multiplication by S in the frequency domain. That corresponds to differentiation in the time domain. Meaning this expression now in this form is just dying to be taken into the time domain. We have the derivative of our input to the plant equaling a weighted collection of errors and their derivative and second derivative. And you'll see that you have in this expression the integral time, the derivative time, and the overall gain K of your system, of your controller. To go from S to Z, let's just use a discrete equivalent with numerical integration strategies of the backward Euler. Let's just now replace everywhere we have an S in that top equation. I just gave you the time domain so you could kind of see what you're doing in the time domain for the analog version. But now let's replace all of those S's with this backward Euler approximation. And now we'll have z's, or z to the minus 1's, floating around. Everywhere we have an s, we're going to replace it with 1 minus z to the minus 1 over t. The first few pieces now, the left-hand side is just, let's approximate that derivative in the discrete time setting. We now have u of n minus 1 over t. And we are going to have some derivatives on the right. K follows down directly. We approximate the derivative of E, the air signal. We don't have to do anything with the middle term. That's just the air at the present time. That's now just E of little n. The last one is a second derivative, and that one gets a little more interesting. In the first pass through this, let's now find an approximation of the first derivative of those two derivative operations on the air. Or now we are saying, oh, we have the first derivative of the air minus the first derivative of the air at n minus 1 over t, and that's now getting us a little bit closer. Now we need to basically approximate those derivatives again, and this is what results. The red curly bracket is now going to be replaced with all of this mess in the last line on the screen. And all we're doing is we are approximating E prime of n, and then approximating E prime of n minus 1, and now you can see that we have the current air, the air one time period before, and the air two time periods before. That now arises out of this second derivative operation. We can now multiply by t, both sides by t, and that gets rid of the t on the left, and it gets rid of most of the t's that are in the basement on the right, and it puts a t in that middle term, 1 over t sub I e to the n. We're going to see a t appearing in its numerator because there's no t in the denominator of that term. And this is now what results. I apologize, you'll be able to put all of this on your piece of paper, but on the screen you're going to not see it. But do you see how the left-hand side now, we've multiplied everything by t, and we're adding u of n minus 1 to both sides, and on the left we have the input at the present time. And don't ask me why I've switched from n to L. The argument of the discrete time index. I was just trying to make sure you're staying awake, because that was probably going to be your question. Where did L come from? I don't know. Down the street somewhere. But it decided to change places with n. But now L is maybe easier for me to write. I don't know. Anyway, if you look at all of these terms that involve E at time n, you will see that you end up with 3 different pieces for one coefficient that weights the air at the present time. And I'm just going to call that alpha of 0. And I haven't shown you all of the other air pieces. They have likewise similar properties, but the air 2 times samples in the past is only appearing really once in that upper expression, and that gives us a t sub d over t. And we are going to simplify that by collapsing all of those combinations of sample period, integral time, and derivative time into 3 different coefficients. We're going to call it alpha sub 0 for the present air's weight, alpha 1 for the previous air's weight or coefficient, and alpha sub 2 for the coefficient on the air 2 samples ago. And with that notation, I can immediately move into the frequency domain or the transform domain by hitting the shift key mainly. I did mention this in an earlier class, but not in here, but in my other class. We're doing Laplace transforms, and I always say, well, how do you take the Laplace of x of t? And I was saying hit the shift key, and you now have capital X. Well, you have to say of s. But anyway, one day, 2 weeks ago or so, I saw a student, and they had a t-shirt, not in my class, but just as I was walking to class, and it said, shift happens. Shift. Make sure I enunciate properly. But as soon as I saw that t-shirt, I thought of Laplace transforms. Anyway, where did that come from? Oh, we have gone into the frequency domain. So shift happens. Shift happens between the top equation and the bottom equation on this screen. And we're now simplifying it a little bit. Maybe you didn't like that comment, but you'll maybe on the final you can say shift happens or something. Anyway, we now are in the transform domain or the frequency domain, and we really are trying to find a more convenient structure with which to think about a PID controller in the discrete time setting. Now let's move the U terms to the left, keep the E terms on the right, collecting those, and I think you can anticipate that I'm now going to find the structure of our controller for the discrete time setting. I'm dividing both sides by 1 minus e to the minus 1. I keep everything in the numerator that was scaling e of z, and I'm going to divide both sides by e of z. That gives me now a controller, capital C of z, in terms of z to the minus 1. Why would I want it in terms of z to the minus 1? Because shift happens, because that's easy to go back into the time domain and write that as a difference equation if you wanted to. If you now had it in terms of these z to the minus 1 operators, you could immediately go back into the time domain and say, oh, here's my difference equation, and I can program that into my embedded system. But here, if we want to think about it in terms of poles and zeros, having it in terms of z to the minus 1s might not be very intuitive. So I'm multiplying by 1 on the right-hand side, where 1 is in red. It's z squared over z squared, to get rid of the z to the minus 2. That's the reason for the red. The red didn't appear initially. I put that in later so that I could now write this in terms of poles and zeros. The denominator now becomes z squared minus z. I can pull out a common z, and now you can see that in this PID controller, I'm stuck with 2 poles. So in designing a PID controller, you don't have to worry about where you place your poles in that PID controller. You've got 1 pole fixed at the origin and 1 pole at z equal to 1. That's a given. What you do have flexibility in are these parameters in the numerator, the alphas and the k. The k is the overall gain, and the alphas allow us to move this quadratic polynomial in the numerator, which defines our zeros of our controller. We can move those around however we want. So that, in fact, if you factored out the alpha sub 0 or combined that with the k, I'm going to call that k bar. Now we have a gain, and we now have a monic polynomial in z. Monic meaning the leading coefficient has been normalized to 1, and now I can form this z minus beta 1 and z minus beta 2 factors to create a PID controller for a discrete time system. On the final exam or on your homework, if I now say design a PID controller, you don't have to go through and find the integral time, the derivative time, The gain, you just now sprinkle a pole at the origin, a pole that's equal to 1. Those are fixed. You don't even get to sprinkle those. You just fix those. And now you get to locate 2 zeros. Those zeros could be real. They could be complex conjugate pairs by the choice of beta 1 and beta 2. Once you've now fixed those 2 zeros, your poles and zeros are on your z-plane. Now all you have left is the adjustment of the gain, k bar, and that moves your poles around on your root locus, which is why we've been talking about a root locus. Here's the pole zero diagram associated with just the controller. If you had a system, the system's poles and zeros would also be joining into this pole zero diagram. But right now, all I'm trying to illustrate in this graphic is a visual understanding of what a PID controller looks like. You simply put down a pole at the origin, a pole at 1. How many more times can I say this? You've now probably zipped through the last 10 minutes of the class on whatever speed YouTube allows you to speed up, right? But now those zeros, I've put them on the real axis, but they could be off. They could be complex conjugate. Why are they complex conjugates? Because you want real coefficients in your numerator, so that if somebody did ask you to implement this, you would have real numbers with which to be gaining things. Here's the process of designing with a PID controller. 2 steps. Well, actually there's 3. I should have put a third step, but I didn't. The third step is adjusting the gain. The first step is introduce 2 fixed poles. And here is a little explanation behind, or the significance of those poles. One pole, if we were in another class, if we were in the analog class, I would say put a pole at the origin. For what reason? For steady state accuracy, to improve the performance of your system relative to accuracy, tracking a reference signal. Here, in the discrete time setting, a pole at the origin in the S-plane corresponds to a pole at z equal to 1 in the z-plane. That pole at z equal 1 improves steady state accuracy. It may make it more difficult to work with the transient behavior of your system, but you do get better steady state accuracy. The one pole at the origin, remember when we had deadbeat response? That was a really fast pole. Well, here we're putting a pole at the origin, or we can think of it as if now we have a causal controller. We're not thinking about or trying to say that we know something before it happens. So our denominator polynomial is the same order as our numerator polynomial with that pole at the origin. That's a way of thinking about that. The designer, that's you. You get to select those 2 zero locations. And those 2 zeros could be real zeros, or they could be complex conjugate zeros, depending on what you're trying to accomplish with your system or the closed loop behavior. Let's look at an example. Suppose somebody gives you the following system or plant, and it's now 1 over z minus 3/4. And you're wanting this to be eventually in a closed loop configuration. Why closed loop? Because open loop is less reliable, less robust. You want the benefit of feedback. So eventually, whatever we do, we are going to translate this or put this G of Z into a closed loop system so that now we have, let's say, kg over 1 plus kg if we just wanted to use proportional feedback. And what would we get out of that process? Can you draw the root locus associated with that? First, what do we want to do if we now have a plant like G of Z? I can hear more movement out of the class next door than I can the class here, but oh. How do we start? Really? I would put a pole in the Z-plane and see what my root locus looks like for just a constant gain feedback controlled system. They didn't invite us to the party, did they? But we could crash it. Maybe. But we don't want this system to crash. Is this system going to be okay with pure gain controller? If you've taken out your cutting board, you know which part of the real line belongs to the root locus. You can now move closer to the origin, which speeds up your system, so you could speed this up with just a pure gain controller in the closed loop setting. That you could locate your pole, closed loop pole, anywhere on the real axis to the left of 0.75 with just a constant gain controlled system. But maybe that's not what we want. Maybe somebody says, you know what, I don't like my error, my steady state accuracy. I'm going to now have, if I put in a reference input of 4, now depending on what k is, I might get out something that's obviously not going to be 4. It might be 3.5, or it might be 5. I now have an error in the steady state. My system might be stable. The transient is going to be an exponential decay. It's going to, as long as I don't crank up k too much. And too much is probably, I don't want to get beyond -1/2 practically. Theoretically, I can't move to the left of -1. If I do, then I'm unstable. So there is a limited range or values for the gain k to keep the closed loop pole that's on that red branch of the root locus inside the unit circle. Let's move away from that and say that you want to design a PI controller. I just basically did a proportional controller. Let's step it up a notch and say, let's design a PI controller. What's the structure of that look like? If you now have a PI controller on the final exam and you're having to design, and I say design a PI controller to modify this, why would we want a PI controller? Now if I put in 4, and if I can stabilize this system, I'm going to have a 4 coming out, aren't I? Because I now have located this pole at z equal to 1 in my forward transfer path. The C of z, G of z block or transfer function now contains a pole at z equal to 1, which is going to give me 0 error to a constant if I keep my closed loop poles inside the unit circle. PI controller immediately gives you that pole factor of z minus 1. But now, in addition to having an adjustable gain, we also have the opportunity to put a 0 in our z-plane. And so now, can you distinguish? Well, I'm going to distinguish between, there's my controller pole. It's going to be red. And where might I locate my 0? You have all sorts of options, don't you? But you can only locate it on the real axis. To simplify your design on the final, you might just say, well, I'm going to cancel that pole. And now I have basically what I had before, except now I have even more bread to deal with inside the unit circle. I've picked up a quarter of a unit inside the unit circle, and what else? Now my steady state accuracy is good due to constant reference inputs. Now I'm guaranteed of having a 0 error due to a constant, and I can locate that pole anywhere on the real line between 1 and -1 based on the adjustment of k. So now my controller PI controller looks like that. And what is my forward loop gain look like? C of z, G of z. My G of z, I started with 1 over z minus 3/4. I've now canceled that with a 0 factor, z minus 3/4. My loop gain for CG is now k over z minus 1. And how do you pick k? Or you could actually say, well, what's my closed loop transfer function now going to look like? Well, that's now CG over 1 plus CG, which if you cancel the common denominator in the numerator and the denominator, you're going to end up with your closed loop transfer function being k over z minus 1 plus k. And your closed loop pole is now resulting from z minus 1 plus k equaling 0, or z is equal to 1 minus k. And you can pick k now to impact the speed of your system, because now you know you have a mode at 1 minus k. If k was 1/2, you would now have a mode at 1/2. So you'd have 1/2, 1/2 squared, 1/2 cubed as far as your transient is concerned, going towards that final value, which is your reference input, whatever that happens to be, whatever constant that is. So here k is selected for the speed of response. Question? So now the question is k still a proportional gain? Yes, so k is the proportional gain, but now you also have this integrator in your process or in your system. You now have a PI controller, but now that PI controller involves a 0 location and a proportional gain. And that proportional gain in this particular case is being used to influence where you might locate your closed loop pole. let's say at 1/2, that triangle. And from this particular equation, you can see that now to get you to a closed loop pole of 1/2 would mean that K is equal to 1/2. Suppose somebody said, well, is this system, this controller, very robust? Have we talked about robustness or what that even means? Is your controller going to still be effective if your plant is not really where you thought it was? Here we thought our plant had a pole at 3/4. Maybe you did a poor, well, not a great job of modeling your plant, and maybe your plant pole was actually somewhere other than 3/4. Let's look at the question then. What about uncertainty in the actual, or maybe you could think of true, location of the pole, or pole location. By that, suppose that here is your z-plane, and let's say that's 1, and suppose that your pole, your true pole, was actually at 0.7. Bless you. So now we have a pole at 0.7. Where did we put our 0 in our PID controller? We located it at 0.75, didn't we? Based on, we thought our plant had a pole at 0.75, and our PI controller had a pole there. Now what's the root locus look like for this? Is it completely different than what we had before, or is it going to look similar? What's the root locus of this look like? Pull out your plastic knife in this room and cutting board with our real axis, and we're splitting it now. Now we have more pieces, don't we? But if you look at that, hopefully you can see that one piece is associated with that pole at 1, moving to that controller 0 at 0.75, and the other piece that actually belongs to the root locus is taking off from the actual pole at 0.7. Now if you gain up the system with the gain that we picked, whatever it was, we picked it equal to 1/2, but let's just say we picked the gain K. How many closed loop poles do you have? Now, how many branches of the root locus are there? How many X's do you see on there that aren't covered up with zeros? You have 2. You have 2 branches. You have 2 closed loop poles. We actually had 2 closed loop poles in the earlier design. It's just one got immediately canceled with that 0 at 0.75. But we still had, so effectively we only had 1 closed loop pole. Question? Why is there a 0 at 0.75? So what I'm doing now is I'm saying we now are trying to determine how robust was this earlier controller that we just designed. The PI controller that we just designed was this. C of z is K, z minus 3/4 over z minus 1. And now we're asking the question, what if my plant was not really what I thought it was? What if the true plant, instead of having a pole at 0.75, had a pole at 0.7? So now we're kind of returning to the earlier design, but we're saying, let's look at some hypotheticals. Let's now see how robust this PI controller is to a plant that might not be as accurately described as what we had it modeled at before. So now the true plant has a pole at 0.7. We crank up the gain to 1/2, and what's going to happen? Well, this is going to get to about the same point that it was before, but now we have a pole somewhere between 1 and 0.75. And that 0 is basically going to sort of cancel that closed loop pole, that triangle between 0.75 and 1, and we're left with the dominant pole with that triangle to the left of 0.7. We're kind of robust. We are robust with this controller for this case. And now I know you're just saying, yeah, but that was when the true plant had a pole at 0.7. What if it had a pole at 0.8? Come on. You have to think about all these different possibilities, maybe. So now we have a pole at 0.8. Is it clear what I'm trying to illustrate? Here is A, true pole at Z equal to 0.7. Now we're saying, what if we look for robustness on the other side? Suppose now our true pole is at Z equal to 0.8, and we're still having to live with the controller, the PI controller that we've had all along. It had a pole. If it's a PI controller, we are forced with a pole there, and our 0 remains at 0.75. What's the root locus of this look like? And you guys all should just be very excited now, right? Now I see hands going. Man, I'm thinking about the restaurant again. Food. This is two poles walk into a restaurant with a 0 to the left, right? You know how to sketch this. This root locus now, these two go together or go towards each other. They break away, and one goes there and the other one goes there. And do you see what's happening? As we crank up the gain K, boom, this is going to just hit, break away, and one's going to go towards the 0, the other one's going to go where we thought we were going before. So now we have a pole here, and let's say a pole there for a choice of gain. Again, that pole is almost on top of the 0 that we designed. That cancels each other out, and we're left with our dominant pole still in the same general area that we had before. This PI controller is fairly robust, and what's it doing in either of these cases? All three of the cases, when the pole was at 0.75, when it was at 0.7, when it was 0.8, what kind of accuracy do we have? We always have 0 error due to a constant, no matter where that actual or true pole belonged or ends up or was, because we have this pole in our PI controller at Z equal to 1. In this loop gain of C of Z, G of Z, that contains a pole at Z equal to 1. And that gives us something good or useful. Questions on that? Yes?
So the true pole represents the actual pole of the plant?
Yes, so the true pole represents, so now we're saying that the true system was in fact that. This was the true plant.
So the 0 3/4 is what we think the plant is
So the 0 at 3/4 was based on an inaccurate understanding of our original system. We thought we were dealing with a plant that had a pole at 3/4. Well, that wasn't quite true. Maybe now the true plant had a pole at 0.7. We looked at that one, fine, or okay. We looked at another true plant that it could have been with a pole at 0.8. That gave us the 2 poles and a 0 root locus, and that was okay. So this PI controller was, I think, have now tried to explain that it's a fairly robust controller for a first order plant that has a pole near 0.75. Question? So now does it lose robustness if the 0, well, the 0 is going to be fixed by the way that we designed it, and now yes, it's going to deteriorate the performance if the true pole, let's say the true pole now was at 0.4. We have a little bit more of an issue, but it's still going to probably be okay. But that's why you need to kind of have a reasonable understanding of your actual system when you're doing the controller design. But here, if we are inaccurate by this amount, 1/2, 0.5 in either direction, we're in pretty good shape. Other questions on that? Yes? So the triangles are there just to illustrate where the 2 closed loop poles are possibly at, based on, we didn't pick a gain, but if you now picked a gain, K, you would know exactly where those triangles were once you used that true plant and your PI controller with a fixed gain K. That would now locate your triangle somewhere on this root locus sketch. And I've just arbitrarily put them in 2 locations consisting with some K value. And if you labeled this accurately, you could now find what K was to get you to one of those triangles, and those triangles might not be consistent with each other. One might really be associated with a K of one value and the other one a different K, but fix a K and you'll get 2 triangles. I don't know if you're having as much fun as I am, but suppose now you pull out another napkin. We're still at that restaurant. And somebody gives you this. Maybe you're being interviewed and somebody says, here's a plant and I want you to design a controller for this particular system. Oh, and by the way, I want 0 error to a constant input. What can you tell the person handing you this G of Z on a napkin immediately? If they hand you a G of Z and they say, here's a plant, control it, what can you say immediately about that plant in terms of its open loop behavior? If you walked up and kicked that system and didn't have any feedback, no control, what would happen? What's the mode? What do I mean by the mode? What would influence its dynamic behavior? The pole, and where is the pole? At 2. It's outside the unit circle, and it's going to go 2, 4, 8, 16. It's going to go big in a hurry. It's exponentially growing. It's unstable, open loop. Can we stabilize it with a proportional controller in a unity output feedback configuration? Yeah, you can, right? This is just this. If we had that pole here, now what's the root locus by? Oh, sorry. They can probably hear me. I'm mic'd up, aren't I? Sorry. You guys listening to this at home, I apologize, but I'm trying to stay awake, and we have some activity in the hallway, and I was just interested. But do you see what the root locus of this looks like? For a unity output feedback configuration with just a gain controller, it's going to push that pole inside the unit circle for a certain gain. You have to crank up the gain a little bit to get you inside the unit circle, and not too much to zip you outside -1. But you can stabilize that system with a constant output feedback controller. Now, that's not going to give us the steady state accuracy that we want. So how do we get zero error due to a constant input? What kind of controller is your next choice? PI. You say, I need to put an integrator in here, and I can do that with a PI. So now we say, okay, we have a PI controller, we have a C of Z, and that has the structure, and now I'm just going to really confuse you. I'm going to say the 0 is at beta instead of alpha. But we have a pole fixed at Z equal to 1. There's our plant pole, and now you've just put a pole right there. Ugh, are you kidding me? Now what have you done? Well, we have a 0, don't we? Where are you going to put that 0? Okay, we're still in the restaurant, right? We don't want to walk out of the restaurant and plop the 0 there, do we? Because then our root locus is going to go there, and that's not a good thing, because now we've fixed that pole always outside the unit circle. So we don't want the 0 to be between 1 and 2 on the real axis. Not sure I'm going to be able to do what I want, but I'm going to try. Doesn't take much, does it? So now what do I want? You don't want to cancel that pole at 2. Why? It's outside the unit circle, and we never, ever, ever want to cancel poles and zeros outside the unit circle. That was Ragazzini. Ragazzini gave us those rules that said, oh, make sure that this 0 factor is in your closed loop transfer function so that we don't cancel an unstable 0. Oh, make sure this 1 minus t of z expression evaluated at the unstable pole is in your t sub, or is satisfied with your t sub c of z expression, so you don't cancel an unstable pole. So we hopefully Ragazzini has taught us we can't eliminate that way unstable poles and zeros, but we can encourage them to come inside the unit circle with what? Our root locus branches by the choice of a 0. And now we know, I kept talking about 2 poles and a 0, but this is why. Now you can immediately draw this picture and say, oh, if I locate that 0 effectively, I can swing those branches of my root locus inside the unit circle. Now, here's my unit circle, and my root locus. Depending on where I put that 0, I know where the breakaway is going to be. It's going to be the geometric mean. But let me just draw something in here. And now we have that for our design. And how do you, well, what have I done? I've tried to select the 0 of my PI controller. I've tried to select beta to produce a desired root locus path. And then K is actually used to fix the dominant poles at a desired location on the root locus. So K is used to fix the dominant closed loop poles. That's the idea. So now let's say, okay, I don't know where I want my 0. I don't want to start iterating on this geometric mean, etc. Can I just pick some desired locations for my closed loop poles and then post calculate the beta value, the location of the 0? That's what I want to do now. Let me try to illustrate that process. So now suppose, for the sake of argument, that the designer wants to have closed loop poles Z delta at 0.9 plus and minus J 0.1. Let's just accept that that's where they want them. So they want what? They actually want these branches of the root locus to pass through those 2 points. By what? Trying to figure out where that 0 needs to be in order to make that happen. Can we now figure out how to pick that beta, the 0 location, based on this now specification? We're trying to answer the question, is it possible to achieve this Z delta with a PI controller? Let me try to draw the picture. There's 1 and 2, and now I'm saying that I want my triangles to be about there at 0.9 plus and minus J 0.1, and I had a pole here and a pole there. And what I'm trying to figure out is what's beta. But if those triangles are on the root locus, what do I know has to be true at one of those points? One or both? Well, it's going to be true at both points, but I'm just going to look at it at one of those. And I'm going to look at the one in the first quadrant. If that triangle in the first quadrant of the z-plane belongs to the root locus, what do I know is true? What do I know is happening right at that location? If that point, if that triangle belongs to the root locus, what did we have relative to the root locus? We had 2 conditions, didn't we? We had a magnitude condition and a phase condition. Which one would tell us that that triangle is actually on the root locus? Or which one would we use to try to establish that? We want the phase to be at 180 degrees at that triangle, and once we know that triangle, which we do, that's at 0.9 plus J 0.1, we know exactly what the angles are from those 2 poles, because those 2 poles are fixed. I now know that I can calculate this angle. This is going to be maybe hard to draw, but I can find that angle. That's theta p sub 2, just using some trig and geometry. I can also calculate this angle These angles are always measured with this positive real line extending to the right from those poles. This is now theta P1. Those are both going to be subtracted away from the angle of my 0, which is right here, and that's now theta beta. Or no, let me just call it theta z. That's the unknown. Can I move that beta around in such a way that the angle theta sub z minus theta P1 minus theta P2 equals minus 180 degrees? And I know theta P1 and theta P2, or I have those that I can calculate. That's what I'm trying to do. I'm going to use the phase angle condition to actually find beta. I now know that the algebraic sum of my poles and zeros, their angles, has to equal minus 180. Or I now know that theta sub z minus theta P1 plus theta P sub 2 is equal to minus 180 degrees. What's theta P sub 2? I always like to calculate the acute angle and take that away from 180 degrees. My acute angle has a vertical change of 0.1, and what's the horizontal distance from that triangle to the pole at 2? 1.1. So now I know that I have 180 degrees minus the angle that has the inverse tangent of 0.1 over 1.1. And this isn't very big. This is now 5.9, whoops, not that big, 5.194 degrees. Or this angle is 174.8 degrees. That's the angle of P2, the pole at 2. And what's the angle of theta P1? And now this may explain why I picked the triangles at 0.9 plus J.1. It's the acute angle is 45, and so now the angle of theta P1 is 180 minus 45, or 135 degrees. I now know everything I need. Theta sub z minus theta P1, which is 135, plus this 180 degrees minus 5.194. And the reason I kept that is because I have this minus 180 degrees over there. So that these two cancel, and I'm left with theta sub z equaling 135 degrees minus 5.194 degrees, or about 130 degrees. What? Is that consistent with my picture? No, but it's still okay, isn't it? What was my angle of theta P1? It was 135, so luckily I didn't go bigger than that and go outside or beyond z equal to 1. If I would, then I would say, okay, that's an unacceptable triangle location. I can't achieve that with a stable closed loop system, because I would have had a 0 between 1 and 2, and we've already said that's not allowed. Why? Why is it not allowed to put a 0 between 1 and 2? You can now convince yourself of that again. We had this and that. Here's 2 and 1, and now I put a 0 there. Now I am locked with a closed loop pole outside the unit circle. So that's not allowed, but this is going to be okay. That 129, 130 is less than 135. So now my picture is a little different. If I make it a little bigger, let's say here is this distance, 0.1, and now my angle of my 0 is bigger than 90 degrees, so my 0 is actually to the right of that triangle. But it's not so far to the right that it's gone past z equal to 1. And what I can now do, I know that triangle is right over the top of 0.9. I'm now wanting to try to find this distance, I can call it x bar, for the location of that 0, which is at beta. So I know that now by trigonometry I can find x bar. I know the angle, I know the vertical distance, I'm just trying to find the horizontal distance. And once I know x bar, I can find beta. In this case, beta is 0.9 plus x bar. And what's x bar? Well, that's just what I said before. Can I now call this theta z bar for my acute angle? Boy, they're not doing very well with resolution on my drawing, but this is now theta z bar. Theta z bar is now 180 degrees minus theta z, or this is now 50.194 degrees. And I know that the tangent of that theta sub z bar, which is the tangent, is opposite over adjacent. The opposite, the vertical height, was 0.1, and the horizontal was my x bar. And I can now solve that for x bar. X bar now becomes 0.1 over the tangent of 50 degrees, which ends up being 0.08, and my 3's can repeat. So that now there's 0.9, here's the x bar, and beta is right there. So beta is equal to 0.9 plus x bar, or it's 0.9833. Whew. So what's my PI controller? I'll do the hard part. You know that's there. You've just found where your 0 is. What's left? Figuring out k. And what do we do to get k? We crank up k until we get those triangles to actually be on top of the triangles that we want, which is at 0.9 plus j 0.1. So this is our PI controller, or that's a specific kind of a phase lag controller. And our root locus now you'll have to humor me. That's now at 0.98333, that 0. What's the root locus of this look like? Well, that's our 2 poles and a 0. And this one probably is not going to be going very far. This now pops over so that we get a triangle there, and we know where that triangle is based on the selection of beta. And what is K? K, we use the magnitude condition to solve for K. So I'll maybe do that offline since we're running short of time. Now you want to get in the hall and start talking. But we can calculate K based on the magnitude condition, and then we have our design finished. And that was now a way to do what? Stabilize an unstable system and still achieve steady state accuracy with reasonable, let's say, behavior. But that's maybe what we'll have to talk about, or maybe I'll talk about that offline. This was a PI controller. If we want to improve the speed of our response, maybe we need the derivative. So I'm trying to now motivate, maybe we now need a PID controller in addition to, or going beyond this PI controller. And we'll pick up at that point next time.